Hi, this is Professor Fernandez. In this video, we're going to work out an example on the limit comparison test. So this example comes from the lecture notes for lesson 7. You can go on to my website to download those lecture notes and a bunch of other good stuff. So let's go ahead and move on to the example. So this one is about the limit comparison test. So in this prompt, I've actually said use a limit comparison test to prove that the series below converge. So in other words, I'm telling you that the series converge. You may not be told the same information when you go out and try to use the LCT in the wild, but this is just for the purposes of getting us started on this lesson. So let's see how we can dive in and use the limit comparison test. To do so, let me just scroll down over here and zoom in here to the actual statement of the test. I'm going to talk about this for a few minutes. So again, this is in the lesson 7 notes for the course. So what does it say? It says, suppose I have two series. Notice right away that I have deliberately left off the starting value for the series. That's because they could start, as we've seen throughout the course, not always at n equals 1. They could start at n equals 4, at n equals 0, right? So the starting value doesn't matter too much in an infinite series. But here are some additional assumptions which do matter, at least for this statement of the limit comparison test. So we are going to suppose that an and bn, the actual formulas for the terms of the series, for all n values, they're positive. So we're looking at infinite series here whose terms are all positive. Okay, and in addition, if I take the limit of the ratio of an and bn, and I get a number which is positive, that's also important, then here's the conclusion, either both of these converge or both of these diverge. So the big takeaway from this new convergence test is kind of exactly what the name implies. So we are comparing two series, both of which have positive terms, and we're using a limit to help us conclude that either both of the series converge or both diverge. And that sets up sort of a nice workflow for using the limit comparison test. So let me go back to the example then and show you what that workflow is. Okay, so let's take a look at example A here. So here's an infinite series that I've deliberately written in to make it look like one that you might recognize, right? And that's going to actually suggest the very first step in the workflow for using the LCT. So this series kind of looks like the infinite series 1 over 2 to the n. Okay, so how did I get that? So vocalizing my thought process here, I just ignored the plus 1. That's literally what I did. I said, oh, this kind of looks like 1 over 2 to the n, and that's exactly what I've written here. And this is the first step. I'm going to number the steps here. This is the first step, really, that I would suggest in you using in the limit comparison test. Find a series that you're looking at, and start with the series you're looking at. Find some terms in the series that you might want to ignore, right? Maybe the plus 1, and again, this will come with time and practice. Which terms do you ignore? When do you keep other terms? And then you will generate another series, and hopefully one of the ways that you know you're on the right path is if the series you generated converges or diverges, effectively quickly just by either looking at it or doing a quick test. So that's the first step. So we have now found a different series. This is our A sub n, our original series. This is our B sub n, our new series. So now the second step is, do I know, right, anything about the convergence of this new series? If you don't, right, then that's a bad series to compare to. You want to find a different series that you either know convergence, divergence for, or can use a quick test to conclude that. In this case, we do know convergence or divergence for this series. You may recognize what type of series this is. This is a geometric series. And if we rewrite this term as 1/2 to the n, then we can tell more clearly that this fits the mold AR to the n, where A equals 1, right? There's a hidden 1 over here. Oops, right there. And R equals 1/2. It's this term here. Okay, so you might remember how the convergence divergence of geometric series works, but long story short, as long as absolute value of R is less than 1, the series converges, and I'll send you over to video 6.2 in this course if you want a refresher on that or work out some examples of geometric series there. Okay, so I'm going to make space for us here and erase all of this because now we know that the series that we have, or we will, compare to is a convergent geometric series. Okay, so that's the second step. First step was identify a new series, which we did here by effectively ignoring terms in the series we're looking at. The second step is to then make sure the series that you've now landed on, that you're going to compare the original series to, converges or diverges using some test or some result that you already know. Okay, so number 3, what's the next step in the process? Here I'm going to start going off and verifying the hypotheses for the limit comparison test. I'll just scroll down here to remind you. What are those hypotheses? First of all, of course, we're going to be dealing with 2 series, so we don't have to verify that, but AN and BN have positive terms. Okay, that's important. And then the second one, I'm going to take the limit and hopefully get that, evaluate the limit, hopefully get a finite number, not infinity or something, that is positive. All right, so let's go back and do that. So scrolling over here. Okay, and so the AN that we started with is 1 over 2 to the n plus 1. So this is a definitely positive quantity for all n, right? There are no negative numbers in sight. When I raise 2 to a power, I get a positive number. I'm adding 1, taking the reciprocal, so that's positive. The Bn that I'm going to compare to is even simpler, right? Just 1/2 raised to the n. That's all positive. So I've verified those hypotheses. Check. So next step in the process, I am now going to find the limit as n goes to infinity of an over bn. Quick thing to mention here, it really doesn't matter if you do bn over an, right? Because all we care about for the purposes of this test is that we get a finite positive number, right? So it doesn't matter if you get 2 or 1/2. They're both finite. They're both positive. Okay, but anyway, we will stick to how we've set things up here. So our an is up here. So that's 1 over 2 to the n plus 1. Our bn is over here. We are dividing by bn. So divided by 1 over 2 to the n. And I've written it that way because this is one of the tests where it's really easy to make small mistakes when you are dividing fractions. Remember that dividing a fraction is the same as multiplying by the reciprocal of the fraction. So that's really helpful because now we are left finding this limit. And I will send you over to video 5.2 in this course to get a refresher on how we evaluate such limits, right? Because, if we look at this, where is the numerator heading? It's heading to infinity, exponential growth. Where is the denominator heading? Also to infinity. So you might wonder, how do I tackle these types of limits that go to infinity over infinity? There is a way to do it with something called L'Hopital's rule, but again, we don't need that fanciness. We can do it with something else called a growth argument that you definitely learned about in Calc 1, and then there's a more formal method. Anyway, so I'm repeating some of what I said in this video. So if not all of what I just said rings a bell, then I definitely recommend taking a look at that video. I'm going to use a growth argument here. So what does that mean? That means I'm going to say, n is going to infinity. So 2 to the n is going to get much, much bigger than 1. So this limit is going to be the same as limit as n goes to infinity of 2 to the n over 2 to the n, right? The plus 1 is not going to make a difference to the value of the limit in the long run, which is n going to infinity. So that's a growth argument. So, and this limit now is much easier to do. These cancel, right? So I'm taking limit as n goes to infinity of 1, which is just 1. So that's the value of my limit. And then now I do my last check for the limit comparison test. Question, is this positive? Yes. And then, implied question, right? Is this a number? Yes, it is a number, right? It's not infinity. Okay, so going back to the conclusion of the test, what is it? Either both of the series, A and Bn, converge or they both diverge. So I'm going to scroll back up and remind you that we had found that the new series, the Bn, geometric series converges. So therefore, this series also converges, right? That's the conclusion of the test. Either both the series converge or they both diverge. All right, so that was the limit comparison test in this example. So part B, I'm going to speed things up a little bit now that we've seen how to do this and what the procedure is, what the steps in the process are. So first step here, again, compare the series to something else that you can tell convergence or divergence for fairly quickly. And how you do that, first step here, we're going to maybe drop a few terms. The most straightforward one that we could drop is the +1, right? We're thinking as the values of n get larger in the series, further into the terms in the series, the +1 is not really going to do much to the sum. So we're thinking that this will be the series that we might want to compare to. And in fact, this original sum might look very close to, in actual value, the sum might be very close to this sum of the second series here. Okay, and this one we can simplify here. So this is n to the 1/2 divided by n squared. N squared is n to the 4/2. So I'm just writing out all of these rules of exponents calculations, right? N to the 1 minus 4/2, n to the -3/2, 1 over n to the 3/2. Okay, quick little just refresher of how you do all this stuff in case you needed it. So this is the new series that we are comparing to. If you are this far into the course, right, this is lesson 7, you may recognize this series. This is a P series. Those series look like 1 over n to the p, where n goes from 1 to infinity. And we learned, and I will send you over to the lesson notes for lesson 6. So lesson 6 lecture notes, right, which you can find again in that site right there. I'll just display it for a minute. You can pause the video and check it out. We learned in that lesson that these series converge for p greater than 1. So the p-value here is the exponent of the n in the denominator. P is 3/2, that's 1.5, that's bigger than 1, so converges. Great, so now we know these series that we are going to use for the purposes of the limit comparison tests, and we know that it converges. So we're all set up for the test. So now next step is going to be starting to verify the hypotheses of the test. So let's go ahead and do that. So what's first? Let me erase the +1 that we got rid of. The first thing to do is, remember, this is the an. This is, oops, make it a little easier here. This is now the bn. So hypotheses are, is an positive? Is bn positive, right? Yes, everything here involves a positive number because n starts at 1 and goes off to infinity. Same thing over here. So check, check. And then next, hypothesis, right? So what do I do with the an and bn? I have to find the limit of the ratio. So an is square root. Let me write over the limit first. So square root, I'm getting there, of n squared plus of n, and then divided by n squared plus 1. And then again, divided by 1 over n to the 3/2. So replicating what we did earlier, that is multiplying by the reciprocal. And then now I'm going to do some more rules of exponents here. I have n to the 3/2 times square root of n. Let's do a little side calculation here. Root n, n to the 3/2. Root n is n to the 1/2. So we have the same base. And so we add the exponents. And we get 1 plus 3 over 2, which is n to the 4/2, which is n squared. So that's my new numerator, divided by n squared plus 1. We're in the same place we were right before. We're finding the limit as n goes to infinity of something that goes to infinity over infinity. So, but again, we don't need L'Hopital's rule. We could do things using a growth argument again. And if n goes to infinity, this plus 1 down here is really not going to matter eventually. So this limit is going to be the same as limit of n squared over n squared, which once again is 1. So last check, right? Is this greater than 0? Question and answer, yes. So then our limit comparison test tells us that both of the series that we are looking at, right, this one and that one, either both converge or both diverge. So this one converges, therefore the one that we started with must also converge. So I'm going to write that over here, converges. Okay, great. And that's the limit comparison test. Thanks for watching.